Okay, thanks, Rajesh, for the introduction. And I'd also like to thank the organizers, Rohini and Swapan, for inviting me to give this talk. Although I should just say at the beginning that I'm not an expert on this area. So whatever I say will be more a broad overview rather than any nitty-gritty details of the subject. Also, I'll not try to give any references because the subject that I'll be describing has been developed by many people over many years. So what you can always find references by searching for the topic. So this is the title of the talk, String Theory and Particle Physics. So let me begin by giving a very broad overview of string theory, a one-slide summary of what string theory is about, okay, or what are its characteristics that will be useful for us. So for the first characteristics is that in string theory, the elementary constituents are vibrating strings instead of point particles. But for the purpose of this seminar, okay, you can just think of string theory as a quantum field theory with infinite number of fields. But most of these fields are so heavy that they are beyond our reach today. Okay, we cannot see them. It has no ultraviolet divergence. In fact, that's what singles out string theories from quantum field theories. It contains gravity. It's consistent in 10 space-time dimensions. And there are 5 consistent string theories which are characterized by the degrees of freedom of the string. Now, of course, every string has its usual vibrational degrees of freedom, okay, which is vibration in 10 space-time dimensions. But besides those vibrational degrees of freedom, each string has some internal degrees of freedom, okay, some motion in hidden dimensions, which you don't see. And this is where the 5 string theories differ. And finally, string theory has no adjustable dimensionless parameter. So the only parameter that a string theory has are the ones that set the units of length, mass, and time, but no dimensionless parameter. Now, even though string theory has no parameter, it has what is called many vacua. Okay, and I'll elaborate on this a little more later. So simplest example is that each of the 5 string theories has a scalar field phi, which is known as a dilaton, with vanishing potential. And because this field has vanishing potential, any constant value of the field is a solution to the equations of motion. And in quantum theory, this C can be interpreted as the vacuum expectation value of this field phi, okay, which will denote by this expectation value. And it turns out that e to the phi, or e to the vacuum expectation value of the phi, plays the role of the coupling constant, even though the theory itself doesn't have an intrinsic coupling constant. And when I say that it plays the role of the coupling constant, okay, what I mean precisely is that we can carry out a perturbation expansion systematically in parts of exponential of the expectation value of phi. So for large negative phi, the theory is effectively weakly coupled, whereas for large positive phi, it's strongly coupled. Now, each of these 5 string theories also has other interesting classes of solutions, besides the ones we described, 10-dimensional solutions. And these correspond to vacuum expectation values of other fields that the theory has, including the metric. For example, the 10-dimensional space-time may be of the form of a product space where it's a d plus 1-dimensional Minkowski space-time and a 9 minus d-dimensional compact space. So total dimension, of course, adds up to 10, as you can see, 9 minus d plus 1. Okay, that's 10. Okay. But of course, you cannot choose this k 9 minus d in any way you like. You have to make sure that this product space that you see here satisfies a 10-dimensional Einstein's equation, because that's what string theory leads to. And once you have solutions of this kind, then the shape and size of this 9 minus d-dimensional space become new parameters that label the class of vacua, besides the dilaton that labels the coupling constant. And in this talk, the vacua will be used in a general sense. Okay. So we'll call a given solution a vacuum if it preserves either Poincare symmetry or de Sitter symmetry, okay, the symmetry of a maximally symmetric spacetime with positive cosmological constant, or anti-de Sitter symmetry, okay, a theory with negative cosmological constant in some dimensions. Okay, so for example, this one preserves Poincare invariance in d+1 dimension. Now, besides the dilaton and the metric that we have touched upon, other fields may also acquire vacuum expectation values if they satisfy the equations of motion. And this depends on the details of which string theory you are considering. So, for example, the two heterotic string theories, okay, of the 5 string theories, 2 of them are called heterotic string theories. They have gauge fields with gauge group E8 times C8 and SO32. And we can switch on vacuum expectation values of these fields along this compact space. So again, subject to the condition that they satisfy equations of motion. And those become parameters, new parameters that label the solution. The other 2 string theories, type 2b or type 2a string theory, has even or odd rank antisymmetric tensor fields. And so we can switch on vacuum expectation values of these fields. So in this slide, you have already learned the names of 4 of the 5 string theories. Okay, the 5th one will appear soon. So E8 cross E8 heterotic, SO32 heterotic, and type 2b and type 2a string theory. So from this description, it would seem that we have 5 different string theories, and each of these string theories have many different vacua. However, there is a property of string theory known as duality symmetry, and that tells us that different vacua of different string theories could in fact describe the same physical theory. So this can be summarized by saying that different string theories in fact are not different theories, but they are different descriptions of some unified underlying theory, okay, which from now on we will refer to as string theory. So here is a very schematic picture of what the situation in string theory is. So you can think of the different vacua of string theory as different objects in some multi-dimensional room. Okay, here of course I have drawn a 2-dimensional room, but this is certainly a multi-dimensional space. And the 5 string theories that I described can be thought of as 5 windows into the room. Okay, and here you see the names of these 5 string theories. So these ones we had encountered earlier, type 2 and type 2b we had encountered earlier. The 5th one is called the type 1 string theory. So these are like the 5 windows into the vacua that are different objects inside the room. And from this viewpoint, we can think of the coupling constant as the distance of the object from the window, so that a weak coupling limit corresponds to objects that are closer to this room, to this window. Okay, so some of the vacua correspond to weakly coupled type 2b string theories, where the type 2b dilaton is small and is large and negative. Okay, so the e to the phi is small. So those are easier to study from this window. Some of the vacua are easier to study from this window, and so on. So now we come to the central question, namely, does any of the vacuum of string theory describe the standard model at low energy? And for us, low will correspond to TeV scale. Now, the short answer is that we do not know yet. And in the rest of the talk, I'll try to give an overview of what we know. So now we turn to the main topic of this talk, namely string theory to particle physics. Okay, how do we try to make connection between string theory and particle physics, in particular the standard model? So let's focus on string theory on this product space, a d+1 dimensional Minkowski space, and 9 - d dimensional compact space. And this will appear as a d+1 dimensional theory if this compact space is sufficiently small. Okay, because you simply then cannot probe this compact space, okay, with finite amount of energy. In particular, if we choose d equal to 3, then this will appear as a 3+1 dimensional theory, and that's exactly the kind of theory, the kind of universe that we live in. And this is the beginning of making contact between string theory and particle physics. Okay, this tells us how string theory can be relevant for particle physics, even though string theory intrinsically live in 9+1 dimensional space-time. Now, any such vacuum will, of course, have gravity, because string theory contains gravity. This I have already said. The question that is of interest to us is, does it have the standard model fields? In the early days of string theory, the most successful solutions were found in this particular string theory known as the E8 times E8 heterotic string theory on a product space like this. And the K6, the particular class of compact spaces that were used for this study, were known as 6-dimensional Calabi-Yau manifolds. Okay, these are spatial class of 6-dimensional spaces that are that actually provide solutions to the string equations of motion. And these were the initial objects of study. So here, because we have these E8 cross E8 gauge fields in 10 dimensions, we can switch on vacuum expectation values of these gauge fields. Okay, and we want to switch on the gauge field components along this compact space, because you don't want to destroy the 3+1 dimensional Poincare invariance. But by doing this, we can break the gauge group spontaneously to some standard model like gauge group. Okay, including SU3 times SU2 times C1, which is exactly the standard model gauge group. We can also get chiral fermions and Higgs fields in the standard model like representation. Okay, in particular, the fermions in the fundamental of SU3, fundamental of SU3, SU2, and so on. So in this description, the standard model gauge group actually comes from one of the two E8s. And the other E8 could be used for accommodating unknown fields or particles like the dark matter. Okay, this was one of the popular models in the early days of string theory, that one used the particles that are living in the other E8 as dark matter candidates. Now, I should say that it is in principle possible to get low energy phenomenology also from the SO32 heterotic string theory and type 1 string theory, which in fact also has SO32 gauge group, but these are more complicated. Now the problems, right? Why aren't we successful in getting exactly the standard model? So the first issue that one faces is that the vacua that were considered initially had space-time supersymmetry. Now, of course, supersymmetry is a very popular topic in study of string, even the particle physics phenomenology, but it's something that is not observed in nature and hence must be broken. And there are indeed suggestions for breaking supersymmetry, but this requires non-perturbative physics. The second issue that arose is that the class of vacua that we discussed are typically labeled by the vacuum expectation values of various fields. This I have already said, like the dilaton, okay, which gives the coupling constant, the shape and size of the 6-dimensional space, and so on. And because these corresponding fields have flat potential, these fields remain exactly massless. Okay, so they appear from the 3+1 dimensional viewpoint as massless scalars. Okay, scalars without potential. These are known as moduli fields. And if these really remain massless, they would typically lead to long-range forces that are not observed in nature. Okay, massless fields typically give rise to long-range forces. Okay, and we of course know of some long-range forces in nature, gravity and electromagnetism, but not, for example, something that is mediated by scalars. So this would contradict what we see in nature. Also, if there are such fields, then they could in principle vary with time or space. And this means that the observed parameters of the standard model will change, because these fields, the vacuum expectation value of these fields, actually fixes what we think of as the coupling constants. Right? For example, if the dilaton varies in time or space, then the coupling constants will start varying with time and space. And this is certainly something that you don't observe in nature. Now, the existence of such exactly flat potentials is typically a consequence of supersymmetry. And one expects that once supersymmetry is broken, these flat directions will be lifted. Okay, they will not remain. The potential will start depending on the vacuum expectation values of these fields. So then the question becomes, okay, once supersymmetry is broken and the flat directions are lifted, is there a local minimum of the potential? And this is certainly needed if we want to describe standard model like vacua, because some point where all the fields are getting fixed. So this problem is known as moduli stabilization. Okay, how to stabilize the moduli, okay, which remains flat at least before you study supersymmetry breaking. And this is in fact a universal issue that arises in all approaches to finding vacua of string theory. And we will say more about this later in this talk. Now let's suppose that we have stabilized the moduli, right? Let's suppose that you have understood supersymmetry breaking and then the moduli get fixed. Okay? Each of the scalars get some particular vacuum expectation value. If this happens, then this will give the values of all the parameters of the standard model, okay, including the coupling constant. And this means that if string theory leads to the standard model, it will give the model with a fixed value of the fine structure constant and other parameters. Now, usually when you do perturbation theory in quantum field theory, okay, and that's one of the most widely used tools that you use in quantum field theory, particularly when you study particle physics. In doing this, we are used to thinking that the coupling constants can be adjusted at will. Okay, of course, nature has a particular values of the coupling constants, but the standard philosophy of doing perturbation expansion is that the coupling constants we think of as adjustable parameters, and we can in principle make perturbation theory as good as we like by taking the coupling constants to be sufficiently small, okay, theoretically. Of course, in nature, coupling constants have fixed values. But this is not the case in moduli stabilized string theory. Okay, even in principle, okay, if you have a moduli stabilized string theory, then the coupling constants are not adjustable parameters. Their values are fixed where the potential has a minimum. So this has in fact a very profound consequence. Okay, this says that even if we are able to stabilize the moduli, we will not have full control over our theoretical analysis if we rely on perturbation theory. Because perturbation theory, okay, assumes that you have the freedom of taking the coupling to be as small as you like, okay, and we carry out a formal expansion. Now, this of course is a limitation of our computational ability, but not of the theory. Okay, but given that at present the computations that we can do are based on perturbation theory, okay, this is a shortcoming that you have to keep in mind. Later we will discuss how the problem of moduli stabilization is studied within this limitation. Okay, but for now we will proceed by keeping this in mind, that there is a limitation, that perturbation theory can never be fully controlled. Now let me turn to vacua of type 2 string theories. So in the early days, type 2 string theories are not considered capable of producing standard model like vacua. And the reason is that they did not have non-abelian gauge fields in d equal to 10. And we know that standard model is based on non-abelian gauge theories. Now, of course, it is possible in principle to get non-abelian gauge theories even if we don't have any in d equal to 10. Okay, even in conventional physics, because once you have a background of this form, then this could generate some non-abelian gauge fields using symmetries of this compact space. For example, if we could get a solution where this compact 6-dimensional compact space is a 6-dimensional sphere, which, as you know, is invariant, okay, has an isometry, which is SO7. Right? You can make a 7-dimensional rotation in the 6-dimensional for this on the 6-dimensional sphere, leaving the shape unchanged. So one can show that in such a case, okay, we'll have a SO7 gauge symmetry. But this is not just not big enough to contain the standard model gauge group. Okay, and that's the reason why type 2 string theories are not favored in the initial days of studying string compactification. Okay, studying the way to get particle physics out of string theory. Okay, but discovery of duality, okay, the picture that I showed you, told us that it must be possible to get bigger non-abelian gauge fields in type 2 theories because heterotic string theories have them. So if a given vacua can be described from all these different perspectives, then given that some of the vacua that we constructed in heterotic string theory had non-abelian gauge fields that can contain standard model gauge group, it must also be the case for type 2 string theories. And indeed, we now know of two ways of getting non-abelian gauge fields in type 2 string theories. One is via d-branes and the other one is via singular geometries. Okay, and I'll describe these two aspects in the next few slides. So it turns out that type 2 string theories have solutions representing extended objects which are called d-branes. So a dp brane extends along p directions, okay, and it's localized in the transverse directions. So in this notation, d0 brane will be particle-like states. It extends only in 0 dimension. A d1 brane is like a string, okay, but this is not the fundamental string that defines string theory. They are a new kind of string. A d2 brane is like a membrane, and so on. So it turns out the type 2b theory has dp branes for odd p, and type 2a theory has dp branes for even p. Okay, for example, type 2a string theory will have a d0 brane, particle-like states. Okay, type 2b string theory will have a d1 brane, which is a string-like object. The second observation that one makes, and this you can show, is that if you have coincident dp branes, then they have non-abelian gauge fields living on them. In particular, if you have n coincident dp branes, then we can get a un non-abelian gauge field in p plus 1 dimension. Okay, because if here is a stack of n coincident dp branes, and what one can show is that on this stack of dp branes there is a un gauge field that lives. Okay, but it's only a p plus 1 dimensional un gauge field because those gauge fields live on the brane. So this gives us new way of getting non-abelian gauge fields in type 2 string theory. And here is the idea. So let's consider type 2 or type 2b string theory on a product space like this. But besides this, let's suppose that we place n d branes, that means d plus 1, the d dimensional branes along md1. Right, md1 is has d space and 1 time dimension. So we imagine that we place this dd branes along md1 placed at some point on this compact space. Right, so here is a pictorial representation. So imagine that we denote the compact space by the horizontal line, okay, and our usual space time, the d plus 1 dimension Minkowski space time, as a vertical line. Okay. So the d branes are extend along the vertical line. Okay, and they are placed at some particular point along the compact space. So this configuration will have some un gauge fields in d plus 1 dimensional Minkowski space, right? And from the low energy viewpoint, they will appear as a gauge theory, un gauge theory. Now it turns out that if we just place d branes, typically this configuration does not satisfy equations of motion. Okay, because d branes carry some charge and the charge has to be cancelled. And this can be done by adding what is known as orientifold planes, okay, which are also extended objects, and they are able to cancel the d brane charge and provide solutions to the equations of motion. Okay. So the orientifold planes should also extend along the d plus 1 dimensional Minkowski space time, and placed at some points on this compact space, right? So here I have denoted pictorially in orientifold plane placed on K9 minus D. Now it turns out that the orientifold planes don't carry its own gauge group. Okay, so if you have a configuration like this, the gauge group that you get is still UN. Okay. But if the D branes are placed at the same point as the O plane, okay, then this orientifold plane can enhance the gauge group. Okay, so in particular, if these n D branes are placed at the same point as the orientifold plane, then the UN symmetry that we see gets enhanced to SO2n, okay, which is a bigger gauge group. So this way you can get SO gauge groups. The second approach to getting non-abelian gauge theories in type 2 theories is to use singular geometries. So far, we have studied geometries where you have assumed implicitly that this compact space is smooth. But now we'll consider situations where the compact space has singularities. Now, normally we avoid singularities, right? Because from the usual particle-like viewpoint that we have, we know that it's hard to study physics near singularities. But it was known from early days of string theory that strings can propagate in some kind of singular geometries without actually filling the singularity. Okay, this is of course not true for arbitrary kind of singularity, but there are certain kind of singularities that the string do not fill. That means it doesn't feel that it's a singular geometry. Okay. And simple example of this are tips of cones, right? So imagine that you have a conical space like this, okay, the surface of a cone. Okay. This geometry is singular at the tip. Okay. And if we try to describe the motion of a point particle through this singular point, okay, typically you run into ambiguities, okay, because you don't know what happens here. Okay. But it turns out that the motion of a string through the tip of the cone is perfectly smooth. It doesn't feel any singularity. Okay, and you can get perfectly sensible answers for motion of strings in such singular geometries. Now, after the discovery of duality, when people started looking for non-abelian gauge fields in type 2 string theories, it was realized that type 2 string theory in certain singular geometries can actually lead to non-abelian gauge fields. In other words, if we take string theory on a geometry like this, md1 times k9 minus d, where k9 minus d is singular, okay, of a specific kind, not arbitrary singular geometry, but when k9 minus d is in specific kind, has a specific kind of singularities, then you may get non-abelian gauge fields. Okay. And the mechanism for this was understood later, okay, and that is the following. Then let's imagine that you have some dp brane. Okay. But this time the dp brane, instead of extending along the d plus 1 dimensional Minkowski space, they now extend along the inside of k9 minus d. Okay, so in particular, let's imagine that this dp brane is extending along some p dimensional subspace sp of k9 minus d. So because these d branes don't extend in the usual observed space-time direction, okay, we can think of these as particle-like objects because they are really confined in this compact space. Okay. So you can think of this as a particle of mass given by the area of this subspace times the mass per unit area of the dp brane, right, which is a fundamental, which is a constant that you can compute. And what happens in the singular geometries is that some of the areas of some of these p-dimensional compact spaces actually vanish. And this means that this particular particle becomes massless because the area is 0. So multiplied by the tension or the mass per unit area, you still get 0. So you get additional massless particles in the singular geometries, and is these massless particles together with the usual abelian gauge particles that of course type 2 string theory has, generate non-abelian gauge particles. Okay, that's the mechanism for how you get non-abelian gauge fields out of singularities. So now let me turn to another way of compactifying string theory, another way of getting low energy physics out of string theory, and that's called the M theory. It turns out that type 2 theory at strong coupling behaves like 11-dimensional theory. Okay, and this 11-dimensional theory is called M theory. The precise relation is the following. Okay, if you take type 2A on say 9 plus 1 dimensional Minkowski spacetime with coupling given by to the vacuum expectation value of phi, okay, this I have already said, then this turns out to be equivalent to, they describe the same physical theory as this M theory on 9 plus 1 dimensional Minkowski space times a circle, and the radius of the circle is given by this e to the 2 phi by 3. Okay, this you can show. And now we see that as phi goes to infinity, okay, on the type 2A side, the theory becomes strongly coupled. But on the M theory side, you get actually a 10 plus 1 dimensional Minkowski spacetime because the circle radius goes to infinity. Okay, so it becomes non-compact space. Now, we do not know much about M theory except that at low energy, it behaves like a well-defined, well-known 11 dimensional supergravity theory. And this, in fact, can be used to study compactifications of M theory. So M theory compactifications, okay, by definition are, you can think of as strong coupling limit of type 2 compactification, okay, type 2 solutions. Okay, except that we get more freedom, okay, because we see that if we start with type 2A on M d minus 1 times K 10 minus d, that becomes M theory on M d1 times K 10 minus d. So if you are trying to get a 3 plus 1 dimensional theory, then M theory offers you a compact space which is 7 dimensional, okay, which is different from what we had earlier, where we had a 6 dimensional compact space. And these give rise to new class of vacua of the theory that you can study, and you can try to study what are low energy physics is. Okay, and many of these also have standard model like physics at low energies. And finally, let me discuss another class of vacua called F theory. These represent the type 2B string theory on the usual class, the d plus 1 dimensional Minkowski space and 9 minus d dimensional compact space. Okay, these I have already mentioned earlier. The only novelty about this class of solutions is that the field phi, the scalar field phi that sets the strength of the coupling constant, actually varies as we move on K9 minus d. Okay, and it varies in a non-trivial fashion. Okay, that in some region of K9 minus d, the scalar field in fact is large and positive, which means it becomes strongly coupled. Now, what is special about this vacua is that these vacua merge the two ways of getting non-abelian gauge theory in type 2B theory. We discussed these two different mechanisms, singular geometries and coincident debraynes. It turns out that in this class of vacua, both these mechanisms can be understood as singular configurations of an auxiliary 11 minus d dimensional space. Okay, so the actual compact space is 9 minus d dimensional, but to describe these, okay, to understand these, the origin of the non-abelian gauge fields, it's useful to consider an auxiliary 11 minus d dimensional compact space, and in terms of that 11 dimensional minus d dimensional space, we can explain singular geometries and coincident debraynes, these two mechanisms, both as coming from singularities of this space. So typically all these vacua that we have discussed so far have moduli fields. Okay, and let me remind you the moduli fields refer to scalars with no potential. But as I have said earlier, to make contact with nature, we have to find ways to generate potential for the scalars such that there is a local minimum of the potential. And this has been most well studied in the context of type 2B vacua, and that's what I'll focus on in this lecture. Okay, I'll not discuss moduli stabilization in other compactifications, although in principle it should be done, but most of the studies have so far focused on type 2B vacua. Okay. So we now turn to the problem of moduli stabilization. So let me begin by giving a simple analogy. Okay, the flux, the notion of flux. Okay. So let's suppose you have an electromagnetic field. Okay, forget about string theory for now, right? Just electromagnetic field. If we have a two-dimensional surface S, we can consider configurations with magnetic flux through S, okay, which basically means that the integral of F on this two-dimensional surface is non-zero. one can show that in order to ensure single valued wave function of charged particles in such a background, the flux must be quantized. Okay, it cannot take continuous values, it must be quantized in certain units. And this is what is commonly known as Dirac quantization. Now, if S is contractible, that means imagine that S refers to a two-dimensional surface surrounding a point, okay, where it can certainly be shrunk to a point. Then we can see that because this integral is non-zero, okay, if this integral is non-zero and it cannot be changed continuously, okay, because it's quantized, then in order for this to be non-zero, F will have to diverge near the point, because the area of the surface is shrinking, okay, as you go close to the point. Total integral remains finite, so F must diverge. And this is what we call magnetic monopole. Okay, and this is the context in which Dirac discussed this quantization law. But we can also consider a situation where S is a non-contractible surface inside this compact space. If that is the case, then integral of F over S can be non-zero, but this can be achieved with non-singular field configuration, because this surface may not contract anymore, right? It can be a non-contractible surface inside this compact space. So this is the idea of flux. Now it turns out that in type 2B string theory, we don't have electromagnetic fields like this, okay, at least not in 10 dimension, but it has two rank 2 antisymmetric tensor fields, which we call B mu nu and C mu nu. Okay, so these are the analogs of the vector potential that you are familiar with in electromagnetism, but these are rank 2 antisymmetric. And for these fields, the analog of the field strength that we had for the electromagnetic field are rank 3 antisymmetric tensors, okay, which are defined here. H mu nu rho is the derivative of B nu rho and totally antisymmetrous, okay, which means you have to add the cyclic permutations. And similarly, F mu nu rho is derivative of C plus cyclic permutations. So because you have this three-form flux, okay, rank 3 tensors, if K6 happen to have three-dimensional non-contractible surface S, we can switch on H and F flux to S. Okay, that's a possible configuration that we can consider. And it turns out that if we do that, if we consider backgrounds, okay, if we consider configurations where we have H and F flux to these three-dimensional non-contractible surfaces of K6, this generates potential for the moduli. But generating potential for the moduli doesn't mean that we have solved the problem, because you have to now make sure that there is actually an extremum. Okay, it shouldn't be an extremum at infinity, for example. But under reasonable conditions, one can show that when the quantized fluxes are not too big, we often get extrema. Okay, it's not there is no hard and fast rule that you always get extrema, but you often get extrema as long as the quantized fluxes are not big. And this is the way we typically stabilize moduli in type 2 compactifications. Okay, switch on fluxes of H and F and then look for solutions for the scalar field. In particular, the modulus correspond to the coupling constant, okay, namely the dilaton e to the phi, turns out to depend on the ratio of the H and F fluxes. So by taking the fluxes appropriately, we can try to ensure that the potential has a minimum at a place where the coupling is small. Okay. And we need this because so that we can trust perturbation theory. But at the same time, we have to keep in mind that fluxes are quantized and they cannot be too large. Okay. So the ratio of the fluxes cannot be made arbitrarily small or arbitrarily big. Okay. So the coupling constant we can try to make small, but it cannot be made arbitrarily small. Okay, because arbitrarily small coupling constant will require large ratios of fluxes, and that is not possible because for large fluxes you don't have minimum. So and the fluxes are quantized. So you cannot have arbitrarily small flux with which you can generate large ratios. So this can be studied, but there is a problem with this, which is the following: that this mechanism does not produce a potential for one particular set of modulus that corresponds to the size of K6. So other moduli are fixed, including coupling constant. Okay, size, the shape of K6 is fixed. Okay, those moduli are fixed, coupling constant is fixed, but the size is not fixed. Okay, there is a potential that is generated by for the size. So we need additional mechanism to stabilize this modulus, the size modulus. And there are two well-studied mechanisms, KKLT and large volume scenario. In KKLT scenario, what one does is that one uses non-perturbative corrections to invokes non-perturbative corrections to stabilize the moduli. Okay. One finds that under certain circumstances, there are some non-perturbative corrections to the potential, okay, of this form, okay, where chi is the modulus. And you can see that as long as A and B are suitably adjusted, okay, with positive values, this does have an extremum where this is of order 1. Now, because the extremum is at order 1, okay, the question arises, are we justified in ignoring the terms that we have ignored, right? For example, what about e to the minus 3c chi terms, right, which will be the next term. Now, that in order to argue that we can ignore this, okay, we cannot have arbitrarily the values of A and B of order 1. Okay. But for example, if A was very small, then we could argue that e to the minus c chi is takes value which is small. Okay. And in that case, we can expect that maybe e to the minus 3c chi terms will be small. Okay, but that requires some accidental fortune that A should be small. In the large volume scenario, one plays the stringy corrections against the non-perturbative corrections. So here the potential, okay, has a power law in chi, and again exponentially suppressed term coming from non-perturbative corrections. And this turns out, again, one can show that this has an extremum of chi of order 1. Okay. And again, by adjusting, I mean, in special cases, if you have these constants appropriately adjusted, okay, then you may get a solution where chi is small, okay, or chi is large. Okay, that's what we need, okay, where the higher order terms are under control. Okay. But in all of these cases, okay, it relies on the ability to somehow find a model where accidentally some of these constants are small. Okay, in a generic situation like this, you lose control. And finally, I should add that in both scenarios, we typically end up with a vacuum with negative energy density, which means we have negative cosmological constant. Okay. But of course, our universe has positive cosmological constant. Okay. And this, again, there is a mechanism that can resolve this problem, that you have to add to this solution that I have described a stack of d branes to raise the energy density to positive value and get the de-Sitter universe. So this is the way one tries to make connection with what you observed, namely a de-Sitter universe, okay, to what kind of solution you get from string theory. Now, based on this study, okay, people have also proposed an idea of why the cosmological constant is so small. Okay. Now, when I say it's so small, okay, in natural units, the cosmological constant that you observe is of order 10 to the minus 120. Okay, so that's a tiny number. Okay. And one can ask, is there an explanation? Okay. And the explanation that has been offered, okay, although I mean it may not be something that appeals to everybody, okay, is the following. Okay. So let's take a typical K6, okay, a typical Calabi-Yau space. It turns out a typical K6, okay, has large number of non-contractible 3-dimensional subspaces. Okay. And we can switch on F and H flux through each of them. Okay. Now let's suppose that the quantized fluxes can take values from 1 to m. Right? I have already said that m cannot be too large because then you don't get a solution. Okay. But m can be up to certain integers, say. In that case, we can see that there are m to the n times m to the n possible configurations of fluxes. Okay. Now, not all of these may lead to actual stable minimum. Okay. But some of them, many of them will, right? Say a finite fraction of them do. Okay, why m to the n times m to the n? Because we can have m possible fluxes through each of these n cycles, right? Through each of these n 3-dimensional subspaces, we can switch on any of the m f flux and any of the m h flux. Now, this can be a very, very large number. Okay, so for example, let's suppose that m is 10, okay, and n is 100. Okay, 100 is actually quite common. The number of in this Calabi house, okay, Calabi house with 103 cycles is quite common. Okay. So we have then 10 to the 200 possibilities with different cosmological constants. Okay. And now the idea is that most of these, of course, will have cosmological constant of order 1. Okay. But a small fraction may have cosmological constant of order 10 to the minus 20, 120, right? Because if you have so many possibilities, then just as a tail of the distribution, we may get some particular solution with small cosmological constant. Okay. And these may describe us. These may describe the vacuum that where we are living in. So one can give a simplified picture of this many vacua by imagining a theory which have many scalar fields with complicated potential with many extrema. Okay, here I have drawn, of course, only one scalar field, but imagine that you have a multidimensional space of scalar fields, okay, and a very complicated potential with many minima, local minima. Okay. And these local minima correspond to these different solutions that I described, okay, stabilized moduli. So this picture is what is called the string landscape. Okay. And if string theory is a correct description of nature, then one of these minima with positive potential should describe us. Okay, positive potential because we know that our cosmological constant is positive. Okay, so maybe this one, okay, is what corresponds to our universe. But one may ask, what is special about that one, right? I mean, why are you here and not here, or here, or here, which has zero cosmological constant? Okay. So this leads to what is the picture of multiverse and the anthropic principle. Okay, and the idea here is that the universe may be very big and different regions of the universe may be in different vacuum. Okay, and for this is quite natural. If you start from a very hot universe and try to study what happens as the universe expands and cools, the possibility that the different parts of the universe are in different vacua is quite natural. Okay. So you may have this situation where different regions of the universe may be in different vacua. Most of these regions have cosmological constant of order 1. Because those are the generic vacua. Okay. But these vacua either collapse too fast or expand too fast. Okay, and they will not be good for development of life in the form we know. Okay. A small fraction of the universe, okay, maybe 1 in 10 to the 120, okay, will be in a phase with low cosmological constant, and we may be living inside one of them. Right? This is what is called the multiverse picture of the universe. Now we come to the last topic of this talk, okay, the swampland. So from the discussion so far, it should be clear that in order to predict the parameters of the standard model, we really need to find the vacuum that describes us. Okay. And this is certainly a very difficult task. Okay, if you believe everything that I have said, okay, they are of the order of 10 to the 200 vacua, and we have to search for one of them, right? That's certainly not possible. Now, I should also add that this is not a viewpoint that is accepted universally, right? That many people argue that no, that most of the vacua maybe actually don't exist because we really don't have control, right? As I have said, that most of these vacua have the problem that the couplings are of order 1, okay, and so you never know whether the terms that you have ignored are actually ignorable or not. Okay, but this is just an order of magnitude estimate that if we just assume that there are solutions, a finite fraction of them have a local minimum, then you get this number of independent vacuum. Anyhow, so finding our vacuum out of this will be a difficult task. Okay. So what the swampland program proposes is the following. Okay. It examines the known vacua, okay, and then it conjectures that the properties that are shared by all known vacua are general principles that must hold for all vacua. And so this means that the values of low energy parameters that do not satisfy these general principle, general relations are not part of string theory. Okay, the string theory cannot give rise to those kinds of vacua, and they are said to be in the swampland. Okay, swampland because they're outside the string landscape. Okay. So if we can identify what the various swampland criteria are, okay, then at least we can say that the standard model, okay, vacua should be not in the swampland, right? That's the prediction that we can try to make. That it's a constant on what kind of parameter values the standard model parameter, what kind of values the standard model parameter should take. and then you can check with what you know. Now, I should say that there is a danger to this program. And the danger is that the vacua we know and can study well are those with unfixed moduli. Because if we don't have unfixed moduli, in particular, if we don't have the dilaton that can be adjusted to make the coupling small, we do not have fully controllable perturbation expansion that we can use. Okay, on all the criticism that I mentioned earlier will apply to this vacuum. So the general lessons that I can draw can be based on these vacua, okay, where we have unfixed moduli. But these general lessons may not hold for the ones where moduli are fixed. And those are the ones that are relevant for our universe. So Swapan program, okay, uses the vacua, okay, to fix some criteria, but those vacua fall outside the class that actually describes us. Okay, so by assuming that these criteria generalize to the vacua that describes us, okay, is a leap of faith, right? But let's suppose that we take this leap and we study what happens, right? So this is a caveat, okay, but with this caveat in mind, I'll now describe some of the conjectures in this program. Okay, there are many conjectures, I'll describe just two of them. The first one is what is called the weak gravity conjecture, and that says that in any string theory vacua with muon gauge fields, there is a charged particle for which the long range gravitational force is weaker than the electromagnetic force. Our vacuum certainly satisfies this. Okay, examples are electrons, protons, W bosons, etc. Right? The gravitational force between two electrons is certainly far weaker than the electromagnetic force between two electrons. Okay, so our vacua does satisfy the weak gravity conjecture. Okay. And all known vacua of string theory, okay, also satisfies this. Okay, so that's one of the conjectures in the Swapan program. The second conjecture that I'll describe is what is called the distance conjecture. And this says that if there are scalars with nearly flat potential, then as we travel a distance of order 1 in Planck scale in the scalar field space, infinite tower of states become massless. Okay, so imagine that you have a scalar field, okay, and you move in the scalar field space, okay, a distance of the order of the Planck scale. Okay. This conjecture says that you cannot move farther than the Planck scale, because then the description of the theory that you're using breaks down, because in infinite tower of massless states, infinite tower of states become massless. So you have to include all these new massless states in your low energy description. Now this criteria actually is relevant for inflation, because during inflation we assume that there is a scalar, okay, with almost flat potential, that's the inflaton. And now we can ask that what can you say if the scalar cannot move further than the Planck scale? And here one uses something called the Lith bound, okay, which requires, assuming that the inflation takes place at a scale that is lower than the Planck scale, okay, Lith bound requires that if we want to produce significant tensor perturbation, okay, then the inflaton has to roll over super Planckian distances. So this seems to say that tensor perturbations are ruled out. Okay, if this distance conjecture is true, then we cannot produce tensor perturbations because the scalar field cannot roll over super Planckian distances. Okay. Turns out that there is a way out of this, and that I'll describe that in the next slide. Okay. And the way out of this is what is known as the axial monodromy inflation. Okay. And in this picture, what happens is the scalar keeps traveling round and round in the field space. So it never travels more than farther than the Planck length, okay, in geodesic distance. Okay. And so it never travels the distance other than the Planck scale. Okay. However, the potential slowly decreases. Okay. And this is of course required by inflation, because as the scalar rolls, the potential should decrease. Okay. And that decrease happens because the tension of some d brane keeps decreasing as a scalar rolls round and round. Okay. And this can produce measurable tensor to scalar ratio, okay, even though the scalar never travels farther than the Planck scale from the original starting point. So this shows that it is not possible to rule out tensor perturbation just based on this distance conjecture. Nevertheless, it gives strong constraint on the dynamics of inflation. Okay, so if it says that if we believe in the distance conjecture and if we observe tensor to scalar ratio in the future, then there will be strong constraint on the dynamics of inflation. Okay, because at least within the context of string theory, the only kind of dynamics that can produce significant tensor perturbation is this axial monodromy inflation. Okay, where inflation just rolls round and round in the field space. Now, I should add that there are several other such conjectures. Okay, some of them are quite wide, but we will not discuss them. The lesson I want to draw from this discussion is a way forward, and I think what we have learned is that given that the details of moduli stabilization cannot be studied fully in the weak coupling approximation, it seems necessary that we develop better understanding of non-perturbative corrections. Right? We really need to understand the explicit coefficients that appear in these non-perturbative corrections to see if we have a controlled, if you can make a controlled study of moduli stabilization. Because if we have the actual coefficients that appear in the perturbative and non-perturbative corrections, then we could in principle check if the terms that are ignoring remain small. But we should keep in mind that eventually we may have to rely on expansion in quantities like 1 over pi instead of an adjustable parameter. This is the price you pay in not having an adjustable parameter. Okay, we expect that we may have some control, but that control is based on an expansion in a small parameter which is not arbitrarily small. Right? The smallness may come from 1 over pi or 1 over pi square or 1 over 4 pi square, but not something that you can adjust at will. So now I'll turn to the concluding slide. And basically what I'll conclude by saying is it should be clear from the talk that connecting particle physics to string theory remains a distant goal. Nevertheless, till now string theory remains the only candidate that can possibly accommodate gravity and other observed forces and particles into a single quantum theory. Thank you.
Hi. So you said that if string theory, this kind of a structure requires that, for example, if you have a U1 theory, then there should be particles for which the electromagnetic force is stronger than the gravity. But let's, leaving aside gravity, is there a way that the experimentalists gathered here can find something which will show that particle physics could not have come from string theory?
That particle physics could not have
come from string theory.
Well, if you could do experiment at Planck scale.
No, I'm talking about realizable thing. So for example, if they find an exotic particle tomorrow, okay, can anything and everything be included in string theory, or are there states that string theory can not admit?
Okay, I think, for example, if they find an exotic elementary particle of spin higher than 2, right, that will basically mean that the string theory must appear at a low scale. Okay, at the scale where that exotic particle is there.
Okay.
Okay, and that means there should be a tower of such particles. Okay, you cannot have a single particle of spin larger than 2, okay, at say TeV scale. You can have bound states, of course, but not elementary particles.
So it has to be larger than 2.
Yes, it has to be larger than 2. I think even if you find spin 2 massive particles, right, that may be enough to make a prediction, because that means that there must be an extra dimension, right? Either
right.
Yeah.
What about if I find something which is a spin 3/2?
Well, spin 3/2 presumably is the
massive spin 3/2 particle.
That is has to be gravity, no, in string theory.
Yeah.
Right.
But so supposing it is a massive spin 3/2 particle, which is not a gravity, supposing it's a charged particle or whatever. So would that say?
Actually, yeah. If you have charged massive 3/2 particle, then that again will tell us
That is
there
not
has to
string
be
theory.
there has to be that string scale is that scale.
Okay,
Right? So there has to be a whole tower.
fine. Thank you.
I have a couple of questions.
Yes.
Regarding them, first, regarding the multiverse and the anthropic principle, if you're truly residing in a false vacuum, shouldn't there be nucleation of bubble and tunneling to an actual vacuum, especially higher temperatures in the early universe? The rate would be enhanced.
Yes, indeed, there will be.
So wouldn't that like invalidate that we're here, or is that rate can be shown to be small enough that we are here?
Yeah.
That we're still in a stable or metastable vacuum.
Yeah. So in typically a generic vacuum, right, will have very short lifetime.
Mhm.
Okay, because that will be nearby minimum. So that's another criteria that will choose between this vacuum, right? We know that we have lived for 10 to the 10 years,
Mhm.
right? So that means the only vacua that are acceptable are the ones that can live for more, at least 10 to the 10 years, right? But I think this picture, I mean, since you brought this up, I mean, one of the predictions of string theory, okay, will be that because you are in a de-Sitter universe, right? That means you have positive potential, okay? And we know that string theory has solutions in negative potential and zero potential. Our vacuum has to be metastable, right? That's a definite prediction of string theory, that we cannot be living in a stable vacuum, right? But the lifetime, okay, of course, has to be calculated, right? Given the defined vacuum will have defined lifetimes. And what we can say is that because you have lived for 10 to the 10 years, right, it should be at least that much, right?
Okay.
Otherwise, they are not candidate vacuum.
My other question is a little bit more outlandish, but are there any efforts to use duality in trying to find something, a theory that is weakly coupled, that is dual to strongly coupled QCD, which could be a really
Yeah. So people
beautiful
have been trying,
prize.
of course, using ADS-CFT, for example, right? Because ADS-CFT, you try to relate weakly, strongly coupled gauge theories to weakly coupled gravity theories.
Yeah.
Right? Except that the kind of theories for which ADS-CFT have been studied are conformal field theories, right? Which are not quite the young males that we want to study, the QCD, right? But this certainly is an effort that many people are making, that trying to understand just usual QCD based on this gauge gravity duality.
Wait, first, John.
Yes.
Yeah, so I had a question which maybe you answered just now, but back when cosmologists started saying that it looks like we were living in an exponentially expanding universe, a de Sitter space, then string theory said, well, no, that's not possible in string theory. Is that still your position?
I think that okay, what is true, I think, in string theory is that a stable de Sitter vacuum is not possible. Metastable one is possible, right? There's no argument against having metastable de Sitter vacuum, and in fact, all this KKLT construction is precisely designed to construct metastable de Sitter vacuum. But yes, so what we can say for sure is that it cannot be stable. So string theory is right.
So you couldn't have a cosmological constant, right? It would have to be varying in some way.
No, it doesn't have a varying in the sense that it could be a minimum. Yeah, it could be a local minimum like this.
Okay.
That's possible. I mean, there are some extreme viewpoints which people, I mean, this is what is called a de Sitter conjecture, which tries to even say that even these are not possible.
Right, that was what I was thinking of.
Yeah, the de Sitter conjecture, but that certainly is not something that is well understood, right? I mean, it's just a conjecture, but it's there is really no firm basis, I would say, for that conjecture.
Okay, that's what comes in your category of wild conjectures.
Yes, exactly.
Okay,
Yeah,
yeah. And then perhaps I could just ask another question, which is related to Debajyoti's question. I remember that back in the day when people were trying to derive things that look like the standard model, in the weak coupling limit, it was not possible to obtain light fields with arbitrary large representations of the gauge group. So triplets of quarks would be okay, but you couldn't get sextuplets of quarks, for example, or you couldn't get, 24-plets of SU5 as another example. Is that still the case in these modern constructions, or is there still a limitation on the size of the representation that you get?
Yeah, I think there is certainly limitations on the size of the representation, but I'm not sure about what the limit is, right? Whether it's still, whether, for example, the 6 you can get, right? 6 of SU3, whether you can get from these new kind of type to be
Sorry,
constructed.
6 was a bad example. Let's go for a larger representation
Yeah,
of it.
so I think if you want arbitrary large representation, there is certainly a constraint that you cannot get arbitrary large representation from these kinds of constructs.
Okay, so that would be another way of disproving string theory if you found one of those.
That's true, yeah. But one has to then work out exactly what that large this thing is. Yeah, that's certainly true.
Can I go now? So the weak gravity conjecture usually is motivated by saying gravity is the weakest force or problems with Planck remnants. The distance conjecture, what fundamental tenet is it based on?
It's based on observation, right? In string, there are many string compactifications that you can study. And in all of those string compactifications, right, which are again have unstabilized moduli which are not stabilized, right? They are flat directions. You find that whenever you go more than a Planck distance, you actually get tower of massless states. So it's basically most of the Swapan conjectures are based on you observe known string vacua, right? What kind of properties they have, and then you try to generalize those properties.
Okay, see, Ashoke, your talk is very popular. So many questions.
Thank you.
You said something that bothers me. You said that if you see tensor perturbations, then that will put severe constraints on the electron dynamics.
Yes.
So, I gave a talk here some time ago. We were trying to work very hard to actually measure early gravitational waves, tensor perturbations. Inflation is just a conjecture, but your things seem to say that it validates inflation, but also restricts electron dynamics. It may not have anything to do with inflation.
True. So what I said is based on the production of tensor perturbation during inflation.
Okay, that's fine.
Yeah. So if there are other mechanisms of tensor perturbation, of course, it doesn't say anything about that.
I was trying to see if we could rule out some of the string theory predictions, but I can't.
If you find tensor perturbation, and if you believe in inflation, then it constrains the dynamics of inflation.
But does it say anything about string theory? String theory predicts string theory has anything other than that? Any other constraints?
Well, I think So
any other constraints you can put on?
What will happen is that if suppose you find tensor perturbation, right? Then
and the spectrum and its amplitude.
Which are big enough, then string theory will tell us that the only class of string compactifications that can give rise to such perturbations are these axial monodromy inflation, where the scalar just goes in a circle.
Okay.
And then you can go ahead and study its consequences, right? Because that's a very special kind of inflation dynamics.
Okay.
For a layman, and looking at this picture, and you would this multiverse, when exactly this multiverse created? I mean, at what stage?
Yeah. So in the early universe, right, the idea is when you are cooling down from a very say high temperature. Okay. At some point, if some region of the universe goes into a de Sitter phase.
So this is before your so-called inflation or after?
Before inflation, say.
Before inflation.
Yeah, before inflation. Okay. Suppose you get into a de Sitter phase, okay, with large cosmological constant. That expands very rapidly. Okay. And as it expands very rapidly, different parts of that de Sitter space makes transition into different vacua. Okay, lower cosmological constant. It's like this. That imagine that you have a vacuum with large cosmological constant, right? You produce some region like this. Okay. It expands very fast. Okay. And then this is of course unstable, so it starts making transition into all these vacuum. Okay. And different parts of this de Sitter space makes transition into these different vacuum. Yeah, that's where this multiverse gets produced.
I just wanted to say regarding John's question, a couple of years ago, there was a talk by Vafa where he gave an example, I think that might answer this. He said that you can write down SU 36 that can accommodate strings, but above N36 that would belong to the swampland. I'm not sure if this is what you were asking, but this is the example that I remembered.
Yeah, it's in the same spirit.
That's the gauge group, but you were asking about representations, but yes, it's sort of in the spirit.
Yeah.
The size of the gauge group is also kind of restricted.
So I understand that with these more modern constructions, the restriction on the size of the gauge group has largely gone away. But yeah, my question was more about the representations, for example, for the fundamental fermions. whether there was a limitation on that once you've chosen your gauge group.
But I think, like Ashok said, there are limitations, but how far? Probably in F theory, there are many. Probably you can go slightly more.
Slightly more, but I think not very much more,
Yeah.
right? To get high representation is hard
Yeah.
in this picture.
Dare I ask another question? Why do we live in 3 dimensions?
Why? Well, I mean, maybe the same idea of string landscape, because if you have a de Sitter phase, right, of the kind that I described, some of the regions of the universe may be in other dimensions, right, where the dimensions are decompactified. And so among these many vacua, right, there are some which describes the 3 plus 1 dimensional big space and 6 small space. And we live in one of those. Probably one can argue that the life cannot exist in 5 plus 1 dimension, but I don't know how solid that argument would be, right? One can try to study this.
The bubble. Yeah, it's fine.
Can this so-called modified gravity theory be accommodated in this string? I mean, some version of string theory?
Yeah, I mean, string theory
Einstein,
normally is able to accommodate a lot of things, but so far, as far as I know, this modified gravity has not been accommodated in string theory.
Okay, yeah, that was a very lively session of question and answers, and let's thank Ashok for a very stimulating talk.